All right, so in this video lesson, we're going to expand on the last one that we took a look at, which dealt with the concept of friction, the force of friction more broadly. And we introduced and talked through some of the key ideas with the different equations. Then, to finish up that lesson with the time that we had available, we went through and we looked at an example of applying kinetic friction and trying to get a deeper understanding of that idea of the coefficient of kinetic friction. Well, we're going to expand on that today with example 2. So this is a continuation of the lesson that we had in the first part of the force of friction. Force of friction, especially with its two parts and introducing some new ideas. This is one of the first ones in our list that we've needed to draw a free body diagram in both the y and the x directions. So we're going to expand on that. That's one of the reasons why friction usually takes a little bit more than 1 day, in this case about 2 days. Okay, so in the last one we had me pushing the fridge and already had it where it was sliding. Instead, this time we're going to look at how hard I need to push to get it started in the first place. How hard must I push to start the fridge sliding? All right, so in this case, I'm going to redraw it here. We've got our same refrigerator, but I am not yet moving. I'm going to start pushing on the fridge, but I'd like to know how hard I need to push in order to get it started. Now, one thing that I'm going to bring up and we'll tie into, actually, let's go ahead and look at those materials. I will give you some important information. One, the mass of the fridge is still about 60 kilograms. Now, that's pretty lightweight for a regular full-size fridge. This is probably better represented by a mini fridge. We found in the last lesson that the coefficient of kinetic friction was about 0.217. I'm going to come in and say that the coefficient of static friction is about 0.40. Now, the first thing that I want to point out is this. I told you to think about this as the roughness, and that's a great way to think about it conceptually, but it's not technically exactly what the coefficient of friction is. There might be some parts where it doesn't seem to make as much sense. So for instance, whether the thing is sliding or not shouldn't really affect the roughness. It should still be as rough as it normally is. But the coefficient of kinetic and static friction are usually different, and static friction is almost always, so far as I know, greater than kinetic friction. And it doesn't take much to actually realize that this is a good representation of real life. So I'll ask you, what's harder to do when you're trying to push something? Get it started or keep it moving? Well, from most people's experience, especially if there's a decent amount of friction, it's always hardest to get the thing moving. And part of that is the force of static friction can oftentimes be a little bit more than the force of kinetic friction because of this fact. The fact that it's harder to get something moving than it is to keep it moving. Now, on a microscopic level, the idea on this is the little bumps and wiggles. You might have a valley where part of the fridge, the roughness of the fridge, part of it kind of sits in the valley. So now you have to push hard enough to actually get it moving up and then kind of overcome that and start sliding over it. If it were already moving, then the object has some momentum where it's more likely to continue going, and so you wouldn't have to push as hard. It's kind of a description for why this functionally happens. In this case, the important takeaway is this. The coefficient of static friction is pretty much always greater than the coefficient of kinetic friction. I can't think of any examples that I've seen where that hasn't been true, but it might be that they're very close. Like maybe the coefficient of kinetic friction is 0.217 and the coefficient of static friction might be 0.230 or something. Usually in a lot of the problems that I've seen in both textbooks and on the AP exam, if the coefficient of kinetic friction was 0.2, then static would be about 0.2 above that. So don't be surprised if you get something where it's like 0.4, 0.6, or 0.6, 0.8, that sort of thing. They're usually spread out by a little bit. Okay, in this case, we saw in the last example how you could go through and get these numbers in the first place. One of my favorite places, or at least it was until I think that there's some automated ads on there now, but was engineeringtoolbox.com. You could go there and they've actually got all sorts of data tables for us to get real life values for a variety of different surfaces. In fact, that's where I got one of the numbers that we'll take a look at in our next example when we're done with this one. So I could look these up online or do an experiment to try and find them. Hint, hint, you will be doing experiments in my class if you're one of my students. Otherwise, check out the lab materials that we've got on one of the other sections, and you can see examples of labs where we actually find those experimentally. Okay, here's what I'm looking for. How hard do I need to push to get this thing started in the first place? Can I get away with only pushing 5 pounds, or do I need to push with 80 pounds? Now, we already have a good idea, since I described it in the last video related to the same things, that it's probably going to be greater than 30 pounds, but I'd like us to have a much closer idea of about where that breaking point is. How hard must I push? In other words, this time I'm looking for an applied force, which is a type of normal force. That's me applying a force onto the fridge. It is common for most groups, including the AP exam and myself, if you're pushing something to maybe mark it as FA instead of just FN, or FP. So FA is for force applied, FP would be force of push, or something like that. But give it a sensible name. Okay. We're going to start moving a little bit faster through these. Especially when I first start out, I try and explain every step very clearly and the reasoning for how I end up getting to that conclusion. In this case, let's talk a little bit about my reasoning, and then we're going to jump into solving this a bit faster. As you get more experience, feel free to move through a bit faster, but don't underestimate how important it is to build those skills and the understanding early on, so that on a simple problem, you may not be thrown for a loop. But I, in the AP exam, will throw harder problems at you, and if you're moving too quickly, we'll catch you. And more importantly, it isn't just that we're trying to catch you to be jerks. We're trying to catch you to make certain that you have a proper understanding of physics so that if you go on to be an engineer, you don't design a car that explodes, or a plane that falls out of the sky, or a building that collapses. Understanding the physics is key to getting this right. Okay, here's my quick reasoning. I'm looking for a normal force, and as we talked about before, there are two ways that you get a normal force. Either you're given it, which we aren't, or you use Newton's second law. Great. That reasoning applies here. I'm going to draw myself a free body diagram so I can visualize the forces. Now I'm going to remind you, we're going to go down the force list, but I'm going to do that inside my head instead of talking about each individual step. So mFg, the mass of the fridge, times the acceleration due to gravity. I've got a normal force holding up the fridge. I am going to be applying a force Fa to the side, but I don't know how much that is. And now, here's where we can talk about the force of friction once again. What type of friction will we be working with? Well, we're probably going to be dealing with static friction because I gave you the static friction coefficient, even though we got the other one from the other example. You may be tempted to say that the fridge is not moving and therefore that's why we're using static friction. That is not the case, however. I mean, it's not wrong in this instance, but it will not always be right. The fridge is not yet sliding. So since there is not any sliding, but I'm trying to slide it, that is our clue that we are actually dealing with static friction. Again, you may be looking at this if you're not familiar with it and going, Sanchez, why do you keep harping on that? Just make it where it's not moving. Keep watching with some of the examples that we've got laid out. The key to it is that the fridge is not yet sliding. So we've got a force of static friction, if you'd like to mark that. FF is perfectly fine. Okay, no ropes, no wires, don't have to worry about air resistance, and we don't have any rockets on this fridge yet. So now I've drawn my free body diagram. The next step is pretty much always apply Newton's second law. Now, forces are vectors, so if we're going to add all of them up, we have to split them into their components. So we need to look at the sum of forces in the x being equal to our mass times our acceleration in the x, and our sum of forces in the y being equal to our mass times our acceleration in the y. All right, well in the y direction, it's actually pretty easy to work with this. We've got the normal force holding the fridge up minus the mass of the fridge times the acceleration due to gravity, and that'll be equal to our mass of the fridge times the acceleration in the y. But once again, my fridge is not falling, nor are we in an elevator, so on flat level ground, this is going to be equal to 0, and we're going to rapidly find that my normal force is once again equal to 600 newtons. I'm skipping a few steps here to keep us moving. If you watched the previous lesson, then you've already seen us solve this. If not, pause the video, plug in your values, and solve for this. Once again, we are using that the acceleration due to gravity near the surface of the Earth is 10, not 9.81, which is a standard thing to do on the AP exam. Okay, so we've got our our y direction. The more difficult part on this one is going to be our x direction. So on this, I'm going to have an applied force, which is actually what I'm looking for, minus my force of static friction, and that's going to be equal to the mass of the fridge times the acceleration of the fridge in the x direction. And here's where things get a little bit trickier, and why I wanted to make certain that we see at least one static friction problem in getting something moving. Asking the question, how hard I must push. Now let's say that I got like a rock on the ground, and I push on it just a little bit, maybe with 1 Newton of force, and it doesn't end up going anywhere. Well, the reason why is there's a force of static friction that if I try and push it to the side, if we were on ice, then it might start sliding to the side, and since it would slide to the right, in this case, not being on ice, having some friction, we would have static friction oppose that sliding and point back to the left, because the rock is trying to slide to the right. If I push on this side, the rock would try and slide to the left, and therefore friction would apply a force to the right to try and oppose that. Okay, but the idea that I'm trying to get across here is this. If I push with a small amount of force, 1 Newton, it doesn't do anything. 2 Newtons, still nothing. 3, 4, 5, 6, maybe by the time I get to 10 Newtons, right around 10 Newtons, it starts sliding. This happens with most objects. You have to push at least a little bit to get it moving, and that's what I'm asking. How hard, and maybe I should say approximately how hard do I need to push in order to get this thing to start moving? So in my example with the rock, well, I could push with 1 Newton of force, and I'm pointed that way, so there's 1 Newton that way, and my quick question is, how hard is static friction pushing back the other way? Well, 1 Newton. And here's the less than or equal to. So let's take a look at that real quick, because it's pertinent for what we're looking at. The force of static friction is less than or equal to the coefficient of static friction times the normal force. I like to call static friction the lazy force. It will do the bare minimum to keep the object from sliding. It will not do anything more than the bare minimum that it has to. Now, if I push with 1 Newton and this can supply 1 Newton, let's say that, in fact, let's go back to my example. Let's say with this together, I found that this maxes out about 10 Newtons. I can do that experimentally by pushing it, and at about 10 Newtons, if it starts moving, I know that the force of static friction maxes out right around 10 Newtons, and that means that this is about 10 Newtons. How do I know that? Because the force of static friction is less than or equal to this number. Well, the biggest it can be then is equal, and therefore, if this starts sliding at 10 Newtons, then this value has to come up to 10 Newtons. But static friction doesn't have to be 10 Newtons. It can be as big as 10 Newtons. So if I push with 1 Newton this way, and static friction pushes back with 10 Newtons, it's going to throw the rock at me. But friction doesn't do that. Friction is opposing sliding. So it's not going to throw anything at me. If I push with 1 Newton, it might be able to be as big as 10 Newtons, but it's just going to push back with 1 Newton. The bare minimum to keep the thing from sliding. If I push with 2, then it'll push back with 2. If I push with 3, it'll push back with 3. And until I get up to 10 Newtons, it will push back and block me. But the moment I push anything more than 10 Newtons, I could push with 10.00001 Newtons, and if that's more than friction, this thing will start sliding. And I overcome static friction, we start moving into kinetic friction, because now we're sliding. Now, that's why I want to emphasize this. When we ask how hard I must push in order to start the fridge sliding, technically we're actually asking approximately how much, or when we say what's the minimum, we should say, in this case, if static friction maxes out at 10 Newtons, we would say, I would need to push with more than 10 Newtons, or a minimum of 10 Newtons, whatever the closest value is on that. But that's what we're looking for numerically and conceptually. So you might actually say, well, if I push with exactly 10 Newtons, then it won't start moving. But what we're looking for is something called a critical point. Critical points happen in a couple of different ways, but one of the most common is when an inequality turns into an equality. In other words, what we're looking at is basically, we want the max force of friction. Well, if the force of friction is less than or equal to our coefficient times our normal force, and we want the maximum value, that would occur when they are equal to one another. And here's the other thing that we're going to do. We're going to substitute in the maximum frictional force to see what the breaking point is. And if I push with exactly that, what's my acceleration going to be? So if static friction can push with 10 newtons of force, and I push with exactly 10 newtons of force, what is the rock going to do? Well, it'll continue sitting there. I need to push with a little bit more than 10 newtons to get it going. We would say I would need to push a little bit more than 10 newtons, or I need to push more than 10, is basically that. But if I match this value, that's the last point, the critical point, where our acceleration in the x will still be equal to 0. So in this case, here's what I'm going to do. I'm going to go back to our equation. Fa minus, I'm looking for the minimum force, the lowest value that I need to push on this to get it moving, and that corresponds as a critical point to the maximum force of friction. And that'll be equal to our coefficient, or sorry, not our coefficient, this is a sum of forces, so that'll be equal to our mass of the fridge times our acceleration in the x. But if I'm matching these two, then this is the last point where my acceleration is still going to be 0, because the rock, or the fridge, will continue sitting there. And when I solve for this, I'll be able to say, okay, if it's 10, I need to push with slightly more than 10. So that's the way that we end up solving these. We have Fa minus the force of friction max, and that's equal to, well, 0 actually, because 60 times 0 is just that. Going back over, we can also look at our equation where we said that the force of friction max is equal to the coefficient of static friction times our normal force. Well, that's going to be 0.40 times 600 newtons. Okay, I'm going to multiply these out. And 0.4 times 600 gives me 240. Yeah, 240. So the maximum force of friction, the biggest that friction can be on my fridge, is 240 newtons. So when I plug that in here, I get the following. Fa, the minimum amount I need to push, minus 240 newtons, is equal to 0. I can add that over, and we get our conclusion that I need to push technically with slightly more than 240 newtons. But since technically the answer could be 240.00001, well, that would just round to 240 newtons. That's why we're kind of giving, that's the breaking point of friction, and that's what we're actually asking for in this question. Okay, so this is how we apply static friction, which is a little bit trickier than kinetic friction. But now we've got that down. We've got one more sample that we're going to take a look at in just a moment. All right, and now for example 3, one where we're going to start combining some of the materials that we've been learning and showing you where we're going to go for things like my test or the AP exam, the sorts of things that we might actually ask, and showing how physics is interconnected, that a lot of things that we study end up coming back and empowering us with other things that we study to be able to solve more and more real-world problems. Now, I'll go ahead and say this. I've actually got this as another video at some point as well. Whenever I had the ability to, I would originally set up example 3 as the following. That being said, we're not going to solve all the parts of this to try and keep this lesson a little bit more on pace. In my actual class time, we don't necessarily have time to do all of the examples, so I'm going to skip straight to the more important one for this. However, hopefully I'll be able to link, if possible, to one of my other videos where I actually solve the numerical part of this. Here's what we've got. I'm driving along in my car, jamming out to my mad tunes, and I'm traveling along the highway in my car, which has a mass mc, and I'm going with an initial velocity v0. Now, in the other video, in the first one that I would normally introduce if we had more time, I would then say that the mass of the car is like 3,000 kilograms and the initial velocity is about 25 meters per second, which is a little under 60 miles per hour, because of course I would never speed on the highway, and neither should you. Safety first, and obey all traffic laws. Okay, and then I would say that up ahead, on say I-35, for example, to no one's great surprise, there is a traffic jam, and cars are at a dead stop. I would then say that we start off some distance away, delta x, and I give a little bit more information, but then we would say, okay, this is 100 feet, or 200 feet, or 60 meters. I'll probably give it a value in meters, but so that you could imagine it. And then we could go through, and my question would be, when I slam on the brakes, will I stop in time? And if so, how far do I end up away from the car in front of me? Or will I not stop in time and run into the car in front of me? And if that's the case, how fast am I going when that happens? In short, we don't normally ask a bunch of questions that you have a 50-50 chance of getting right. So we're not just going to say, do I hit the other car? Because you could flip a coin and maybe get lucky. So what we'll say is, okay, if yes, then show me that you could actually solve for that by finding this number. Or if no, then show me that you could solve for it by finding this other number. So those are things that you will probably end up seeing, and that's part of the reasoning why we do that. On top of that, our entire purpose is to check that you know how to apply the physics. Okay, and that being said, we would then go through, we would solve all of it with real-world values. That is a place where I mentioned in earlier in this lesson, or the last one, that I talked about going to engineeringtoolbox.com to actually get the coefficient of friction between my car tires and the road. So in this case, I'm going to just say that that is mu. I believe normally for car rubber and concrete, they usually design those to have very good traction, good friction. So we actually have something along the lines of 0.8, maybe 0.9, sometimes some groups even quote 1, that we get really, really good traction between those. Okay, but in this case, we're going to go through and we're going to do a derive. We're going to derive an expression. So I'm giving you all of these things in variable form. Okay, so here's what I want. I provided you the following. I have said that we have a car with mass mc. It has an initial velocity v0. It has a coefficient of friction between the tires and the ground of mu. I guess I should give that some subscript so that it's specialized. Mu sub c for the car, or I guess t for tires, but I'm going to tie everything to car if I can. And I want to know how far the car needs to come to a stop. If I could find that, then I'd be able to tell, okay, well, if I've got that much space between me and the blue car, I'm fine. Or if I don't have that much space, I need to turn the wheel and go off the side, possibly into a ditch. I'd like to avoid that if I can. And my car's suspension would be grateful for that too. Okay, so here's what you would see on my exam or the AP exam. Your instruction word would be derive. This does not mean take a derivative, but it does mean that we're going to do representational mathematics. And my students, I expect that that's a uniform approach or a universal. My students usually do not like the derive stuff, but it's not going away. The AP exam and any of the physics exams that I had seen at the university level, they all ask students to actually do a lot of deriving, even though it's not calculus. Okay, so derive an expression for delta x in terms of mc, v0, mu c, and constants as appropriate. Now, a lot of times this will actually say and universal constants or and physical constants as appropriate. On the AP exam, they usually use that notation. And there is a list on the front cover of the exam booklet that actually tells you a list of universal or physical constants. Anything on that list you can answer just in terms of, you don't have to put that number in. For our purposes, I'll go ahead and tell you this right now. Physical constants basically means you can answer in terms of g. So g is allowed. In general, physical constants are if you Google it and it's always the same number. So if you Google the acceleration due to gravity near the surface of the Earth, it's always the same number. We would say that it's 9.81 meters per second squared, or newtons per kilogram in magnitude. So if it's always the same number, usually that's the case. There are other things that might be a constant for a given problem, like the coefficient of friction between the car's tires and the ground is probably a constant number, give or take, but it's not always the same for each car or each thing. So mu sub c, mu is not always the same number. G, at least on Earth, is. And that's kind of the distinction between them. Okay, now I want to emphasize this because we're going to see this when we get to the end, and I really want to emphasize it here. What they're asking is, We want delta x equals some stuff, and the only things that are in it are either math or these allowed variables. Now, the other thing that I want to emphasize on this is just because these variables are allowed doesn't mean they have to be in the answer. And we're going to see how that might manifest in this problem. Okay, so this is what we're looking for. And I want to emphasize this, especially if you are new to deriving expressions. Don't worry if you don't know exactly where you're going on this. And this is one of the reasons why so many students have a hard time with physics, because they're used to, just give me a checklist and I can go down that checklist. I know how many steps there are left, and I feel comfortable because I'm doing something that I've just done before. But all that's doing is having you memorize some stuff and then throw some numbers together. That's not actually problem solving, that's just monkey see, monkey do. The thing about physics is it's unsettling at first because when you're used to having a nice straight path that you could follow every single time, it's unnerving to be thrust into a position like this where you're asking me for a thing, I've worked with things like it before, but I don't know what steps I need to take. That can be really overwhelming for students. And that's why it's important for us to get this practice now and get these skills. It's not easy, and that's one of the reasons why this is so hard. Physics is renowned for being challenging, but when you understand physics, you can go on to do things like be an engineer, be a scientist, be a doctor, be all these things that aren't easy. Not everyone can do that because not everyone pushes themselves out of their comfort zone to begin working problems that they don't already know how to solve. That's how we advance as a society, how we advance scientifically in particular. If all we ever did was look at problems that we already knew the answer to, we'd never invent something new. And so this is unsettling, and I do want to emphasize that. If you are completely new to this, or still relatively new, you probably don't like it, and I don't blame you. But I can tell you, I was just like you when I went through and started with this. When I got my physics degree, I remember thinking in my head multiple times, just give me the numbers, I don't want to have to derive it. And then I got more and more used to it, and now I'll never go back. I start off almost everything by doing derivations. Okay, now that I've done a plug for that, let's go back to actually solving this. Okay, the same techniques that we have been studying since day one are exactly how you approach this, admittedly, more complex problem. Okay, I'm looking for delta x equals some stuff. I need an equation with delta x in it. Oh, okay, well I've got a whole bunch of equations actually. Technically, we probably want to look at our kinematic equations. Right now, that's the only thing that we've studied that has delta x in it, but that's a great place to look and where we're going to start. So if I'm going to work with kinematics, I'm going to organize my variables just like we learned in kinematics. Okay, so going down the list, first off, identify what it is you want. We want delta x equals some stuff. Great. Now let's start filling in information that we know or think we know. Okay. Let's see. Ooh, the initial velocity. I know the initial velocity of the car. We were told that it's v naught. I don't know the acceleration. I don't know how long it takes to come to a stop. I don't know how far I go. Final velocity. Final velocity. So my goal is to come to a stop. We're trying to find an expression for stopping distance. And so my final velocity is going to be 0. So that's another thing that I do know. Okay, I want an equation that has delta x because I need that to solve for it. I want to include both of my velocities. And now I need to know, because I don't know the acceleration and I also don't know the time, but here's where I can think about additional information that I've been given and, honestly, the section that we're working in. I was also allowed to answer in terms of a mass and a coefficient of friction. Well, when I look at that information, I can see, well, that would be useful dealing with some forces. And at least from what we've learned right now, which of these two things would forces help me out with? Would it be acceleration or would it be time? In this case, here's how we can say, oh, we're probably going to try and find our acceleration using some force stuff. So for now, I'm going to say I know nothing about time and I have no plan on how I could get it, so I'm going to use the equation that does not have time in it. Well, that would be our fifth kinematic equation, and it is v final squared equals v initial squared plus 2a delta x. In derivations, whenever you have a value that is 0, put that in. Make your life easier. So we get 0 equals v naught squared plus 2a delta x. My goal is to get delta x equals some stuff. So I've got delta x here. I'm going to get it where it's on the side by itself and then solve. So I'm going to subtract over negative 2a delta x is therefore equal to v naught squared. And to get delta x by itself, I would divide both sides by negative 2a. V naught squared over negative 2a. Okay, I have delta x equals some stuff. Am I allowed to answer in terms of v naught? Yes, I am. Am I allowed to answer in terms of negative 2? Yes, because that's math. Am I allowed to answer in terms of a, the acceleration? No. Okay, so we're not done yet, but I do want to emphasize this, especially if you are new at deriving equations. You don't necessarily know where you're going, even when you're not new at it, you don't necessarily know. And so a lot of times people will get this far, which is great, and they'll think, oh, I've wasted my time, this isn't my answer. You haven't wasted your time. We're getting closer, and now we have a plan of attack. We need to get rid of a. We need to somehow replace a in our expression with something that is allowed. So, I need more information about accelerations. Well, here's where Unit 2 comes in. Where do we get accelerations from? Why? We get them from Newton's second law. Our sum of forces will be equal to our mass times our acceleration. Okay, well, in order for me to actually predict the acceleration, I'm going to need to look at all the forces acting on the object, so my next step is a free body diagram. I'm going to go down my list, but very quickly. We get mcg for the force of gravity down. We're going to have a normal force holding the car up. And here's where we have to stop and think a little bit. If you haven't really worked with cars before or thought about them, how they work, when I ask what makes a car move forward, most of the time students go, well, the engine does. And while that's technically true, the engine isn't pushing the car. And I can prove it to you. So you hit the gas and the car moves forward. That's normally what happens. What if we take it into the shop and we lift it up on blocks? You can turn the car on, the engine's going, and you hit the gas, and you can see the wheels spinning, and vroom, 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 but you don't go anywhere. The engine of a car doesn't push on the car like a rocket engine would. A rocket engine can push without you being in contact with the ground. That's what makes it a little bit different, and it's a force of thrust. For a car, it's actually the interaction between the wheels and the ground that actually allow it to go forward. So when I slam on the brakes, I lock the wheels in place so that they can't spin anymore. At least that's what happens if you don't have an anti-lock brake system. We'll come back to that. In this case, we're going to say that what I've done is I've slammed on the brakes, and that eliminates any forward force from the engine, because the engine can't push me forward if the wheels aren't allowed to spin. So I'm going to slam on the brakes, I lock the brakes, and my wheels are not spinning, and therefore I'm just going to slide. And we're going to say that we're using kinetic friction, and I'm sliding to a stop. So, since I'm sliding to the right, my force of friction is to the left. And here's one of the things that I want to emphasize on this, because a lot of students run into a problem with this. They'll say that the car is moving, and therefore something has to be pushing it forward. But there's nothing pushing it forward. It continues moving forward because of Newton's first law of motion, because of its inertia. But that's not a force. And I won't go into great detail on it, but I do want to emphasize it. It's not a force because inertia doesn't come from something else. Remember, Newton's third law says forces always come in pairs shared between two objects. So if there was a force of inertia pushing you forward, where's it coming from? Nothing's pushing you. So while it is a thing, it is not a force and does not go on your free body diagram. In this case, this is actually the correct free body diagram. We have a net force to the left, meaning we're going to have an acceleration to the left, which means I'm going to slow down and friction is going to bring me to a stop. That's why I need that net force. If you had something forward, then they might balance each other out and I would continue moving at a constant speed. Something to think about. Okay, no ropes or wires. While technically drag force would be a part of this, we're going to ignore that. And I don't have any rocket engines on my car. And even if I did, I'd hopefully turn them off in this case. Okay, so jumping into this, I can do the following. I'm interested in the acceleration, which is in the x direction. So I'm going to jump straight to my sum of forces in the x. And that'll be equal to my mass times my acceleration in the x. And that's actually going to be my acceleration here that I need to replace out. So I've got negative force of friction is equal to our mass, mc, the mass of the car, times my acceleration. the same acceleration that we would use in our kinematics. In short, the force of friction is slowing me down. It's causing the acceleration that's making me slow down and come to a stop. Friction is stopping me. That's what this equation is saying. Okay, great. So now I've got this, although I can now move this around. I'm going to divide both sides by mc, and I get my acceleration is equal to negative force of friction divided by mc. Okay, great. Well, this is my acceleration, so I can plug it in up here. Going back to my equation, keep my eye on the prize. I have delta x is equal to negative v naught squared over 2 times a, which I could write as force of friction divided by mc. Okay, great. Delta x equals some stuff. Negative is allowed, v naught is allowed, 2 is allowed. Force of friction isn't. But mc is. So, again, don't get too frustrated. We are making progress. Now I need to find out how to get rid of my force of friction. Oh, we have an equation for that. Our force of friction is going to be equal to our coefficient of friction times the normal force, how hard the surfaces are pushed together. This normal force. In the y direction, I would have normal force minus the mass of the car times the acceleration due to gravity equals the mass of the car times the acceleration in the y, but my car is not jumping up off the ground, nor is it sinking down into it. So my acceleration in the y is 0, so this whole side becomes 0, and I can add mcg over to the other side. My normal force is therefore equal to mcg. Taking this, I can then say that my force of friction, being kinetic friction, is equal to my coefficient of friction, mu c, times my normal force, which is mcg. Now that I've got my force of friction, I can go back to my equation. We said delta x was equal to negative v naught squared divided by 2. We said a could be replaced with the force of friction, but I now know that the force of friction is mu c mcg divided by mc. I've replaced the force of friction, this thing, ff, with what it's equal to, and I put it in here. Now that's a mess, but we're done. Watch. Delta x equals some stuff. Great. Minus, that's a math thing, that's fine. V naught, I can answer in terms of that. 2, that's math, I can answer in terms of that. Mu c, that's allowed. Mc, that's allowed. G is allowed from physical constants, and mc is allowed. Done. You don't even have to clean this up. In fact, right now, some people may be saying, well, you have a denominator, a fraction in the denominator. Your math teachers may have you clean this up. We don't ask you to. Now, if you have the time and you want to, it might make it a little bit easier on the poor grader, but this is perfectly acceptable. You have a correct answer. Now, I am actually going to take us through a couple things on this, though we are done. If this is a test, you get here, you have the thing that I've asked for, equals some stuff, and everything is allowed. You are done. You can move on to the next part. But we're not on the test. And apparently, I'm trying to teach you all things. So we're going to expand on this just a little bit because it might prove useful. First off, look, I've got mc divided by mc. The mc's actually drop out. So delta x actually equals negative v naught squared over 2 times mu c times g, because the mc's canceled out. Remember how I said at the beginning that you're allowed to answer in terms of mc? That's why you could leave it with mc in there, but you don't have to. You can also have a perfectly good answer that does not have everything that you're allowed to answer in terms of. There are plenty of problems where we say that you can answer in terms of something, and it doesn't necessarily show up in the answer. We just say that we would accept it if it was there. Many times it's actually the mass that ends up falling out. Okay, last thing that I want to talk about with this, because I introduced it, so we might as well take a look. We've got delta x equals negative v naught squared over 2 mu cg. Now, I will bring something up. You may be worried about the negative here, but in this case, it was actually because remember that we have an acceleration, and therefore the acceleration is pointed to the left. So when you plug in all these values, you'll actually end up with a positive when you track them with the proper values. The thing that I want to focus on instead, however, is the units. Well, delta x is measured in meters, so on the left-hand side of the equation, we have meters. We have equals meters per second for our velocity squared, so that's going to be meters squared per second squared, we'll come back to that, over 2, well 2 is just a number so it has no units, mu Here's why I mentioned a big deal about mu not having units. It also doesn't have units. So the only units on bottom come from g, which is meters per second squared. If I were to rewrite this, I would end up with meters squared per second squared divided by meters per second squared. The divided by second squared on both top and bottom cancel out, and one of the meters cancels out, and we are left with all of this mess has the equivalent units of just meters. Meters equals meters. It is not only a possible equation, it is the correct equation. What we're looking at, it's unpleasant at first, but I want to emphasize this because, hey, write this down. It may solve some problems. Here is the general solution to a car stopping, the stopping distance for a car on flat level ground. All right. That's all we have time for in this lesson. If you get the chance and want to see this with numbers, where especially the negative gets worked through when we actually have the numbers in there, then I'll try and link that other video. But this is the key material that we wanted to cover in this lesson. Until next time.